During Taylor's Zoom course. So if you want to join this Zoom, okay, so the ID is 896 something. Okay, this is a passcode. Okay, done. Okay, so okay, before I start this lecture, I go back to the academy. So so by this week we get 10 students. Maybe have one more exchange. This means from last lecture we didn't miss any students in this lecture as so far. So okay, I think this is going to be good news. I hope by after we finish the first 2 weeks, after the ed and job period, we still have 10 students roughly. So, okay, so before I start, I still wish to quickly go through the teaching plan. So for the first week, okay, okay, we have finished the fundamental concepts for the first week. We talk about the concept of navigation and also introduce a little bit about the Wi-Fi RTT. So we introduce the range-based Wi-Fi RTT positioning and also the signal strengths. We call it fingerprinting based Wi-Fi positioning. So for today, so we are going to finish a little bit about the components we remain from the last lecture, and then we are move to the first part of the satellite navigation. So in terms of the satellite navigation, we have around we have around 3 lectures. So I want to emphasize. So for week 4, okay, 26. So we are going to have no lectures. Okay, that's good news, right? So no lectures for week 4. So we are going to have 3 weeks to introduce the satellite navigation. Okay, so the first one is like for today. Okay, we are going to talk about how to use the satellite measurement to do the positioning. Okay, so for example, you are okay walking around the campus. So how to use the satellite measurements to localize your position. Okay, in 3D. Okay, so for week 3, okay, we are going to talk about not only the positioning problem, okay, also talk about the velocity estimation. So for example, based on the satellite measurement, how to estimate your velocity, okay, with the satellites. Okay, so for the week 5, almost the last lecture for the satellite parts, okay, we are going to talk about the high accuracy GPS positioning. So for example, for week 2, we are talk about the positioning with accuracy of around like 5 meters. Okay, 5 meters. So for the week 5, we are going to talk about the high accuracy GPS. So we are going to achieve like 5 centimeters. Okay, something like this, maybe 5 centimeters of accuracy, okay, for positioning. So after that, we have one more lecture or one more tutorial, I can say it's a lab, okay, for GPS. So after that, we are going to talk about the visual positioning midterm. So this roughly about the, okay, so at the beginning of each lecture, I'm going to review the teaching plan to you, like take 1 to 2 minutes to, in this case, you are going to have an image. So where we are currently at this stage in terms of this whole lecture. So also, I want to emphasize a little bit about the because the university have emphasized for several times in terms of the ground rules. So if you enter this classroom, okay, so please speak English. So because this is the media language for teaching, okay. As long as you enter this classroom, so like within 3 hours, okay, so speak English. So and also arrive on time. So as I mentioned last week, so some of the lectures you may have some experiences like some of the lecturers they take attendance, okay, with the QR code they take attendance. But in this lecture, I'm not going to do this, but still, if you want to attend on site, okay, physically be here, so please be on time, okay, please be on time. But still, according to the guidelines of the campus, we still have we are going to provide the video recordings, but I'm quite sure on site Performance should be better, okay? Okay, so let's move on. So last week, okay, let's quickly go through the content we have talked about last week. So, okay, we mentioned that we have several TAs. Okay, we have several TAs. So those are ground rules. We talk about the assessment criteria. So we have midterm test. We have a group presentation. Okay, the final exam is open book. So we get 2 assignments. So for the first half of the semester, we get 1 assignment. So for the second assignment, it's going to be coming from the second half of this lecture of this course. So, and also those are the basic requirements. For example, in last week, we provide some example codes for the Wi-Fi positionings, right? So you need to, so because in the last lecture, you mentioned that majority of you have background in Python. So I said, I just assume you already have some background knowledge for Python. So if there's no, should be okay. So because I mean, our example code is quite easy to understand. You can just learn from ChatGPT or I mean learn by yourself. I mean this is our requirements. So also I mean for the actual time, okay, for the actual time. So mainly I mean for the homeworks because we have 2 assignments, right? So and also if you really want to, so for example, if you provide some example codes by Python, right? So if you want to improve it, of course you can spend extra time, okay, to improve the readability of the codes or maybe the accuracy. Okay, that's what you can invest your time, okay? So those are teaching plans. So I'm going to just, okay, so this, for this GitHub, I strongly suggest you to make good use of this page. So for example, okay, before I start this lecture, I get 2 issues. So for example, like how to debug code with the Chrome. So I found a solution. Okay, I change this with this. Okay, to Python something. Okay, this Chrome back. Okay, easily to in the code, run the code by Python. So what I want to emphasize is please make good use of this page. So the issues and a lot of learning materials or the examples are provided in this page. Okay, frequently check this page if necessary. So those are the introduction we mentioned last week for the Wi-Fi DT. Okay, we mentioned several 2 different methods. The first one is like a range based. So for example, we get a range. For example, this is a router. Okay, this is a Wi-Fi access point. Okay, so I can get a range from the access point to me. Okay, let's see the distance, right? And also the location of the Wi-Fi router is a non-variable. So in this case, I can calculate my position. So this is the range based. So the second solution is called fingerprinting. So for each, for example, for example, like the white box for this one. So for example, if this is a Wi-Fi routers, so if I use a receiver to like collect the signal from this router, so generally the signal strength transmitted from this router to me should be a kind of fixed value. So for example, if the signal strength from this router is kind of like 35 dB hertz, so during the transmission, because there's no reflection, no blockage, so the signal strength should be quite strong, right? So based on this, the similar principle, we can get a signal strength map of the plane. For example, like at each of the grids, for example, we can divide this room area, okay, into several grids. So for each grid, we should able to get the signal strength, right? So based on this, we can get the signal strength map. So for example, like, okay, for the, you generate this map, right? So for the second time I enter this room, for example, today I generate this signal strength map. Okay, so for tomorrow I get into this room again. I also receive a signal strength from this router. So possibly I need to find, for example, the strength is like 35 dB hertz. Should be maybe like normally it should be coming from the blue area. So this is kind of matching. By matching the signal strength map together with the exact signal strength you received from the router. So this is the, for example, based on one signal, you can have several candidates. Okay, for example, the blue parse. So also you receive a signal strength from different routers, maybe 4. So you can make a decision, okay, to find the most consistent location, which should belongs to your exact location. So this is the concept of the signal strength. So the phone name is like received signal strength indicator. So let's represent the signal strength. So the strength is denoted by the colors. So usually the signal strength is around like 19 to 32 dBHz. So for example, this is the routers, right? As you know, you can still connect to the Wi-Fi if you get into another rooms, right? Because the signal can go through the walls. But this is for communication, it's okay. But for positioning, it's different because the signal strength is attenuated by the walls. So for example, if the signal strength during the signal transmission is like 32 dBHz. So if you receive a signal from another rooms, okay, with a wall, with corridors, so the signal strength may be like just around 20 something. So this signal strength reduction is due to the attenuation coming from the walls. So this is the physical meaning behind, okay? So any questions? So based on this, you can do some like fingerprinting. So we can sorry the fingerprint okay, you can say like the fingerprinting is like you can say this is a term okay used for to define the Wi-Fi signal strength based positioning. What you need to understand is like this you can understand this term as the map of the signal strength. Okay, this is easier to understand. So in this case, we can use the signal strength to do kind of the matching. So as I emphasized last time, I not really going to like, for example, okay, for the Wi-Fi positioning, we have 2 solutions, right? The first one is range. The second one is a signal strength based. Okay, so I'm not going to provide the example for this one. Okay, so but I provided examples for range based. So for example, this is the examples, right? So for example, this is the location of the Wi-Fi routers, right? So for different red dots, okay, this is the location of the Wi-Fi routers. So what I want to estimate or what I want to calculate is the location of, the green points is the exact location of the users. Maybe it's a smartphone. Okay, so what I receive is the location of the 4 red dots. The location of the Wi-Fi routers is a non-variable, and the distance from this router to the receiver is also non-variables. So it means you get 4. It's you're going to you get 4 equations. So in this case, you can solve it iteratively. For example, like if you only have 3 routers, you'll be good enough because you only need to calculate XYZ. So for example, okay, go back to the equations. So maybe this one is easier to understand. So for example, okay, so TX2 and TX1 is the location of, for example, okay, from left side, the TX2 and TX1 is the locations of the routers, okay? So the location is, represented by X2, Y2, and X1, Y1, okay? So, and also range, the yellow dashed line, okay, the R1, R2, this distance is the range between the user and the routers, right? So this is also a non-variable. So based on this, we can have 2 equations. Okay, this is the basic distance, the square distance, right? So in the 2 equations, x1, x2, y1, and y2 are the non-variables, right? And on the right side, okay, r1, r2 is the distance. This is also the non-variables. So based on these 2 equations, we can do some movements to get this. This is directly coming from the 2 equations. So we can make this into a matrix. So if you look into these equations, so xy is the unknown. R is also associated with xy. So in this case, you can solve this equation by solving this matrix, right? So make the inverse, you can solve these equations. So it's going to be like it's going to be like x should be equals to a inverse multiply b. So in this case, you can solve x. So you may get get the question in your mind. So why not directly solve this equation, and why we need to refine these two equations into the matrix? So for example, if we are not talking about two signal transmission, so for example, we have 10 or 20 Wi-Fi routers. So it means you are going to have 20 equations. It's almost impossible to solve this equation, okay, based on what you have learned from high school. You're going to be crazy. For example, in a final exam, make this question, you're going to be crazy, right? You cannot solve it by handwriting based on 20 equations. But for the metrics, for the computers, they can do this. So for example, MATLAB or the Python, they can easily do the calculation based on the metrics. So they can solve it efficiently, even there are like more than 20 routers. Okay, so this is the review for the lectures previously. Okay, so those are different levels of devices. We call this like smart devices, like a smartwatch or some smartphones, like from Xiaomi, from Samsung, from Google, like Google Pixel. They all support the Wi-Fi RTT measurements. Which means like if you take a smartphone from Samsung or from Xiaomi, if there's some Wi-Fi routers over there, you should be able to get very accurate positioning. Indoor positioning. Okay, should be. For example, like I just one more sharing. So for example, if you go to like K11 supermarket, for example, if you want to find some shops, if you directly open your smartphone, okay, if you close the Wi-Fi and close the Bluetooth, it's going to be crazy. It can even, your smartphone can never locate which building you are. So if you open your Bluetooth, kind of better. It depends on if there are some beacons for Bluetooth in. Beacons means this is the infrastructure. It depends on if this shopping mall provides these facilities. If there's no Bluetooth, okay, you can just open your Wi-Fi to connect to the Wi-Fi. Immediately, you're going to like the Google map will tells you which shopping mall you are. So this is at least the power of the Wi-Fi. So, but still, majority of the shopping malls, they may not directly accessible Wi-Fi network to you. So in this case, it's still, the indoor position is quite difficult, a problem at this stage. So for example, for your smartphone, besides the Wi-Fi and Wi-Fi and Bluetooth, they also use the 5G, for example, like 4G or 5G and LTE signals. So those different radio signals can all be used for the positioning purpose. Okay, so let's roughly all for the Wi-Fi RTT positioning. This is another case we also mentioned. Okay, so for example, if this measurement is different, so TX2, TX1, this is the signal transmitter. Okay, you can say this is a Wi-Fi router stuffs. So in here, okay, the XY, this is the location of the receivers, right? So the location of the receiver is unknown variables. But from the previous slide, the measurement, the signal or the measurement is the range, right? We get R1, R2. But for this case, the measurement is the angle. So it tells you what is the direction of the signal. It's quite different. Because some of the sensors, they may not directly provide you with the range. Range means the distance. They provide with the direction of the signal, the theta 1, theta 2. Okay, so it means the unknown variable is xy. So the known variable is theta 1, theta 2, together with the location of x1, y1, x2, y2. So in this case, we can also quickly obtain this equations. Okay, let's turn the theta subject to the left side. So we can also arrange this into the matrix. So finally, we can solve this equations x. Okay, should equals to equivalent to the A inverse multiply B. Okay, so this is another model. If the measurement is not the range, we are going to have the angles. So how to solve it? It's kind of similar. Okay, so let's move back to the outdoor positioning. Okay, just now we have talked a lot about like Wi-Fi, like those angle of arrival. So we are going to, okay, let's start from is the GPS. So intuitively, the GPS, okay, so in here we have the GNSS. So the GNSS is the aggregation or the combination of the different satellite system. So for example, we have GPS, right? So for the EU, for Unions, we have get the Galileo. Okay, for Russia, they have the GLONASS satellite system. So the combination of different satellite system, we call it GNSS. So Global Navigation Satellite System. So the GPS is, of course, this from US. So the GPS positioning is based on the triangulation. So what is triangulation? So for example, this is one satellite, right? So for example, okay, based on a given distance, okay, we can have a triangle, we can have a circle. So for another satellite, for example, if we receive the signals from three different satellites, so the intersection of the three circles is the exact location of the receivers. So for example, this is the receiver's location, this is the distance, okay? We call this distance as shoot range. So later, okay, we are going to introduce this. So this is the distance from the receiver to the satellite. So by drawing three different circles, okay, we should be able to get the intersection point. So this is the unique point. Okay, this is the position of the receiver. Okay, so for the GPS positioning problem, okay, the location of the satellite, this is the known variable because we already know the orbital information of the satellite. So, and the distance from the satellite to the receiver, this is also a known variable. This is what you receive. This is called GPS signal. Okay, you can directly get the distance information from satellite to receivers. So the location of the satellites is a known variable, right? So the distance from the satellite to the receiver is also a known variable. So what you want to know is the location of the receiver. So it's quite similar to the Wi-Fi based problem, right? So in this case, if you get three measurements, okay, you should get the three different square distance equations. So by solving the three equations simultaneously, you should be able to get the location of this receiver. So the problem is like in the future, we mentioned we have different satellite systems. So usually if I just in the seaside, typically I can receive more than 40 satellite systems, 40 satellite signals, maybe 10 from GPS, 10 from BD Beidou, 10 from GLONASS, 10 from Galileo. So in this case, you're going to get 40 equations, right? You cannot solve it by yourself by your hand. So in this case, still we need to have some intelligent solutions to solve it using a matrix by computers. Okay, so at this stage, you may have a question. So how to get the distance? Okay, for example, like the radius of the circle, how to get the distance from satellite to receiver? Any ideas like how to get the distance? So you may recall like, sorry?
Time difference multiple.
Exactly, yeah. This is based on time difference. So in the last lecture, okay, smart guys. So for last lecture, we mentioned like for the Wi-Fi DT, this range is based on the time difference, right? So this is exactly the same. So for example, the signal is transmitted from the satellites at time, maybe like T1, and after several nanoseconds or milliseconds, the signal is received by receivers. Okay, so this time difference is maybe like 1 or 2 nanoseconds, multiply the speed of the light. So this is the distance. This is the distance. But the problem is like, this time difference is based on the assumption is like the clock of the receiver and the satellite is accurately aligned. This is the assumptions, right? So for example, if in the old days, we have the mechanical watch. After like several months, it may not be accurate because the clock will drift. It's the same. If you take the smartphones, the clock in your smartphone is not as accurate as the as a satellite, because in the satellite, the clock is atomic clock. It's kind of like never drift over time. It's very expensive, but actually never drift. It means for different satellite system, their time are aligned because they all use the expensive satellites. But from user side, okay, my smartphone, okay, I use the Android smartphone, you use the Apple smartphone. Of course, their accuracy of their clock are different, right? It means there is a clock differences between those satellites and the users. But the good thing is, for all of the satellite system, okay, they have the shared clock bars, clock differences, because all those satellite systems they have very accurate atomic clock. Okay, you understand like this. So in this case, you need to calculate the XYZ, right? This is the location of the receivers. Also, I just mentioned later clock differences. And the clock differences, this is the error terms. This is included in the distance measurements. So in this case, you also need to simultaneously estimate the clock differences. But no worries, okay, later we are going to have equations to show the principle behind. So in this case, at least you need 4 satellites. It means 4 satellites means 4 satellite measurements. You have 4 square distance equations, right? So for one satellite, okay, you have like x s minus x receiver blah blah something. Let's for one satellite provide 1 equations. So 4 satellite provide you with 4 equations to solve the 4 unknown variables x, y, z, together with the clock differences between the user and the satellites. Okay, so basically this is the profile or the overview of the satellite positioning. Okay, so finally let's see the receiver's location. Okay, quickly get to this location. So this is just for illustration. I mean, in practice, they will not intersect to one point because there are some errors in the measurement. So for example, the satellite signal have a lot of error terms, maybe by the refractions, by the ionospheric delays, tropospheric delays. Okay, we are going to have detailed models in the future. So those are the different levels of the GPS receiver. So as you know, so the autonomous driving industry, like the Google's autonomous driving cars, so those are already been like quite hot for around 10 years, right? So I mean the automotive industry grows from 2016 something to now. But I mean, if you really look into the startup companies or like Google, so Google working on the autonomous cars, but they never make profits in this branch, in this business model. But for those companies, they are designing the different receivers. They make a lot of money. You see, this is the differences. If you're working on the whole system, like automated cars, they never make profits at this day, at this moment. This is a good dream, but maybe it's like far away from. But for those companies, they design the GPU, NVIDIA. Okay, this is the biggest company in this world at this stage, right? I'm not sure today, but 3 days before they get job. So NVIDIA, they products, they produce the GPUs. They sell those GPUs to those companies like Google, Waymo. So okay, they earn lots of money. It's similar for the GPS receivers. So those companies they earn quite a lot, quite a lot. So for example, those for different levels of receivers. For example, the most low-level receiver is the GPS, it's the smartphones, right? So for the smartphones, it's quite compact. So if of course, I mean the receivers for this smartphone should be low cost, right? So for low cost receivers, the consequences, the accuracy is not guaranteed. Okay. So for example, like for the receivers, for the GPS receiver chips, for example, like the Huawei or like Apple, for example, if they buy a GPS chips together with the GPS receiver, so you guess how much they need to pay for to Qualcomm or Broadcom? You guess? Actually, just like five US dollars, $5. But within this $5, they need to pay additional $2 to Qualcomm and Broadcom additionally because they need to pay for their patents. anyway, for example, like for each of your smartphone, you have paid like around like at least like $10 to Qualcomm and Broadcom. This is amazing. It means that Qualcomm they just do nothing at this stage. You need to pay for them. For those receivers, it's quite similar. So those are Qualcomm, Broadcom. Okay, those are receiver producer in US. So for the you can say this is the low level smartphone. Okay, this is the low level. So for this is the high level for the commercial receivers. So for this one, like Ublox. So this is a company in Switzerland. Okay, so they produce the low cost GPS receivers for the cars. So for example, they have sell a lot of chips, a lot of like modules to different autogen cars and also like Jones companies. So for example, previously DJI, okay, DJI, all the receivers, all the GPS receivers are coming from Ublox, yeah, because it's quite low cost and also provides kind of satisfactory accuracy. Okay, so for this one, okay, maybe this is $500. Maybe this one, I mean, in massive production. I mean, for like Google or Xiaomi, okay, if they have the massive production, they can make this into five US dollars. So for this one, it's like maybe 500 Hong Kong dollars. Okay, 500 Hong Kong dollars. But for this one, it's like more expensive. This is the geodetic level. Okay, geodetic level. So usually maybe used by like, you know, in PolyU, we have a department, it's called SGI Land. What's the full name of SGI? SGI department, Land Survey Geodetic Information. So their department have a lot of lectures about the geodetic. So they have a lot of receivers of this level. It's quite expensive. Okay, maybe like 20K Hong Kong dollars something to buy a receiver. Okay, so this because this is too expensive, they are normally not massive production for the autonomous driving industry. So this is for different receivers. So if we do, if we decompose this receivers, it can be like this. So this is the antennas, okay, to receive the radio signals from sky. So this is the front end. So front end can do some signal acquisition stuffs. So this is the computers to do the processing. Okay, maybe you can use the MATLAB. So as I mentioned in the last week, maybe in the future, the Python will gradually replace the MATLAB. You use the C plus Java to like the Android smartphones. You can use the Java. Okay, Android smartphones you can use the Java to do the positioning. So if you look into the accuracy, so the problem of GPS, as you know, the signal will be like kind of reflected by the buildings, right? So in this case, the distance ranging, okay, it's going to be vast. Okay, includes a lot of the error terms, like how much the signal is reflected with additional transmission delay. So this is the errors. So for example, okay, this is one of the scenarios in Hong Kong. Okay, let's take a look. Okay, so the errors using different GPS positioning methods. Okay, the errors, I mean the horizontal position error. Okay, horizontal means 2D, 2 dimension. The error can easily reach about 84 meters by GPS. 84 meters for GPS. And for example, if you use some differential like high level technique, it can kind of improve, but this is still like more than 20 or 40 stops. This is not acceptable for the auto-driving cars, right? So this is the big errors. So that's why, I mean, for example, like in my group, we have students working on the scientific problems of GPS, like how to improve the accuracy of GPS. So if you look into the left side, this is signal reflections, right? So this is a plot. How to understand this plot? So for this gray area, so I mean those circles with numbers is the index of the satellites. So for example, those green, it's like, okay, there are two tall buildings. Okay, if you look into the sky, you only have a like very small area that is visible for the sky, right? So this is the area. It means for the gray area, it means it's coming from the building area. It's blocked. So for example, if those satellites are located in the gray area, it means those satellites are all reflected. should be coming from this phenomenon or this phenomenon. Okay, so in this case, what you receive is only the green satellites. As a result, the first problem is like the signal quality is terrible. The number of the satellites you can receive is significantly reduced because of the blockage. So this is the real case. Okay, the accuracy is around like maybe more than 20 meters. So another method is called directing. So for example, if you have IMU, so you can do a directing to, so the IMU, so for example, this is the IMU sensor. For example, if you play smartphones, right? Yeah, you can, I mean, the smartphones can help you to sense the orientation of your smartphones to help you to play games. So the IMU, the full name of the IMU is the inertial measurement units. So it includes IMU includes two components. The first one is called the accelerometers. So it can provide the angular acceleration, the acceleration of three different directions. For example, three different directions, right? So for second component is the angular velocity. Sensor can provide the angular velocity, speed, angular speed. So based on the two sensors, we can, for example, okay, based on the acceleration measurement from the IMU, you can calculate the change of your velocity. So by doing the 2 times of the integration, you can get the change of the positions, right? So for example, acceleration, you get the, by doing the 2 times of integration, you should be able to get the change of your position. So for example, okay, by accumulate this change gradually, okay, you should be able to infer your trajectory. So this process is called directing. So for example, for this, okay, this is starting point, okay? So by doing, for example, 1 second, okay, move forward for this direction with a given distance. For next seconds. But the problem is like the error will accumulate. For example, there are some like 2 centimeters of error from this motion inference. And also for this one, maybe 2 centimeters. So those errors will accumulate until the current constant is right. So the dead reckoning can provide the inference of your motion change, but the problem is like it will accumulate the errors. Okay, so this is the general concept for dead reckoning. So let's see the example. Okay, so for example, we can like stick the the IMU sensor to your foot. We can gradually to sense. So for example, if we lift up our foot, there are some accelerations in the sensors. So in this case, you can continuously. So for example, if you move forward for 1 length, usually for example, if I go like this, for each stride, it's around like 0.5 meters, right? By accumulate this motion change, you should be able to infer your trajectory. So for example, if you install the IMU sensors like in your fridge or maybe take your smartphones, because inside your smartphones you also have the IMU sensors in your smartphones. So mathematically, it's going to be the position at time n should be equal to the previous position plus a change. But the problem is like if there are some errors in the delta x, it will accumulate with time goes on, isn't it? It will accumulate over time. But the problem is another one is that you also need to get your headings. So for example, given a certain distance, I can go this direction. I can also go through this direction, but the angle is different. So for example, if you want to calculate your trajectory, if the angle is not correctly estimated, it will also affect the calculation of the x. So the theta here, this is the heading angle. So this is usually provided by the magnetometers in smartphones. Okay, this can provide the headings directly. So for example, in this process, this is called pedestrian directing. Pedestrian, people walking, pedestrian. So directing means to reckon your position, based on your head, you just go like this, but accumulate all those motions simultaneously, you get the trajectory. So this process, the input is the accelerometers. Accelerometers provide the accelerations. in three different directions, right? So by doing the 2 times of the integration, you should able to get the change of your position. And also for the gyroscope, this can provide the change of the angles. This is called angular speed. For example, like how much you have rotate with respect to the vertical direction. So this is the measurement from gyroscope. So for the magnetic meters, okay, this can provide the heading angles with respect to the north direction of the Earth. Okay, so based on this 3D information, we can generally get your position. Okay, this process is called prediction directly. Okay, so in here I only provide a general concept about PDR. Okay, so it's no need to like really dig into the equations. For example, like in this case, for example, how to detect you finish your step. Okay, a lot of details inside. I mean, so still this page it only provides a general concept for the prediction directly. So this is the example. So if I put my smartphones, okay, 1 step, 2 step, 1 more step, of course you can get a jump in the accelerations, right? For example, if I lift up my foot, I get the accelerations in the sensors. So this is the jump of the accelerations. So in this case, by detecting those peaks, of course, for example, 1 peak means I finish 1 steps, right? 1 peak, 1 steps. In this case, you can accumulate those steps. You may have one question in your mind. So if you accumulate all those steps, the accuracy is kind of like not good. But no, in the urban canyons, we have mentioned the GPS error is around like 20 to 30 meters. This PDR can make a big differences for you. Can make a big differences for you in terms of positioning. So based on this accelerations, you can get the change of your motions. Okay, so this is for PDR. Also, you can like install install the IMU sensors or smartphones to the fuse. The detection of this jump is going to be more distinct, more easier to detect the steps, detect each step. So the step detection. So step detection definition is detect the dip of the vertical acceleration data as 1 step. This. Okay. So any questions for this page? Okay, take a break for 5 minutes. Actually, this PDR happens almost every day in your smartphone. Every day, you take your smartphones, it happens every day. For example, like smartwatch, they have the healthy monitoring process, like functionalities, right? So how they calculate your steps? It's based on this. It's based on this. It happens every day in your smartphones. Yeah. Yes. I mean, the prerequisites. So I did get your point. You mean before you start, before you learn this lecture, do you need to learn, if you need to learn avionics, not on the morning. I mean, the prerequisites for this lecture is limited. Especially for the mathematics parts, I'm going to provide a lot of details. Should be okay. Also, the final exam is open book. Oh, yes, final exam is open book. Yes. Oh, you sent email to me? I was in the last week you are not attend. Oh, okay, I see. So we have a presentation in the last 2 weeks. We had 2 weeks to do presentations, and each like you can put groups like it's like 2 ways. Also, you can make an independent presentation. It's okay. So you can make a teamwork. It's also okay. So each your presentation is like 20 minutes, around 20 minutes, 10 minutes away. Say like this. Don't need. Yes. Oh, the presentation we are going to provide several topics for you. Select. Also, you can select some topic that is out of the book. The basic requirements is should be relevant to this topic, this course. Navigation styles. Like you can talk about the Jones navigation or the Tesla navigation style, like the Google's auto-train cars, like you can talk about how they do navigation styles. Okay, it's quite nice. Oh, yeah, use three or you go? Use three. ATE. AE. Okay. What's your name? Sahad. Okay, I try to remember all the students' names. Yeah, it's okay. Of course. Okay, so let's go back. In here, we provide some examples like, okay, so this is one for the work on the PDR. I mean, take smartphones and with smartphone inertial sensors, MU, we can do the directly. So this is the testing scenarios at PolyU. So for example, I mean, take a smartphone at the text mode. Okay, text mode means, okay, chatting with your girlfriends, boyfriends. Okay, just walking around. Okay, so let's take a look how this PDR looks like. Okay. So this is a ground truth. So ground truth means this is a reference trajectory. This is the exact trajectory how you walks around. Okay. So in here we provide for different solutions. So this is the I mean you can understand like the 3D PDRs. It's a conventional methods. So we have row NIN. So this you can understand this is a artificial intelligence aided solution. So, I mean, look into this trajectory can make a comparison. So, of course, this one is more accurate, right? I mean, the overlap. So, because this one should be the same trajectory. Okay, the same trajectory. So, at least, I mean, for this one should be much more accurate, much more accurate. But still, I mean, if you go for a short distance, I mean, accuracy is kind of okay. But if you go through a long trajectory, I mean, accuracy is, I mean, it's going to be drift over time. Okay, let me like it will drift in 1 meters in area 100 meters distance. Okay, so this is roughly the results looks like. So of course, in this research, I mean, in this results, we only use the MU based PDR prediction directly. So of course, in the future, you can combine more sensors into the like to do the positioning. You can combine the GPS, you can combine the inertial measuring units, also combine the MU together with the Wi-Fi to improve the accuracy. You can do the sensor integration. So this is one for results. So for example, I just mentioned the upper right side results, the area is around like 1.8 meters, 1.9 meters for the relative position errors. So this is roughly the results. But still, I mean, this value will, I mean, increase if you travel for longer distance. Okay, if you travel like more than several kilometers, it will significantly drift over time. So another sensor, this is called light detection and ranging. So this is the typical sensor that's used for the autonomous driving cars. So okay, this is the overview of the measurements from the lidar. So for example, okay, the lidar can provide a dense point cross, right? So this is typically this is installed in the Google's autonomous driving cars. So the principle is like this. I mean, for the single channel lidar, okay, the simple case, this is the laser signal emitter, right? I mean, this is signal transmitter, okay? So if this is reflected and received by the receivers, okay, so the distance can be calculated based on the time of differences, right? This is very similar to the GPS. So for example, the time differences from this to this multiply the speed of the light. This is going to be like a double of the distance, right? So in this case, you can calculate the distance from this object to this sensor. So if we look into the 3D LiDAR, okay, for example, like this signal is transmitted and reflected by something, finally go back to this LiDAR sensor. Okay, this is corresponding to this components. So again, I mean, the time differences multiply the speed of the light equals to the double of the distance from the object to the receivers. So this is the basics of the LiDAR. So for example, the equation is like the distance is equals to the speed of the light multiply the time of flight over 2, okay? So over 2 because it travel for like double, okay? Double of the exact distance. So for example, okay, so the LiDAR can do the positioning as well. So for example, this is the typical sensor setups of the auto-train cars. So this is the LiDAR, okay? Roof-mounted LiDAR. And also there's a GPS receivers, GPS MU, and of course we have some batteries, and okay, so let's say the dynamic systems, engine system. So also we have some ultrasonic sensors, also some radar sensors to do, like for example for the high-end cars, they also have some like some intelligent collision avoidance systems. So this is based on a radar sensor. So in terms of the cost, for example, okay, I teach this lecture, I teach this course, guidance navigation for this is the 4th years. At the first year, okay, the sensor, the cost of this one maybe is like 0.5 millions. In the second year, it becomes 0.3. In the third year, it becomes 0.2. So by this year, the cheapest case, the LiDAR is only like 20K something, 20K or 40K something. You can see this is a significantly decrease in terms of the cost of the LiDAR. So, but also, like several years before, because the LiDAR is too expensive, the massive production of the auto-driving cars is still far away from. But currently, we can see some clues that the auto-driving cars is coming to our life because the cost of the sensors like LiDAR reduced significantly over the past years. So there is a term, it's called LiDAR odometry. So LiDAR can also use it to do positioning. So I'm not going to dig into the principles. So generally, the LiDAR can provide the relative motions. So for example, if the car is driving driving forward, okay. So LiDAR will provide the 3D point cross of the surrounding from different time steps. So based on those information, so the LiDAR odometry algorithm can infer the change of your motion, over time. This is the LiDAR odometry. So the procedure of the LiDAR odometry is like, so the impulse is the point cross. So for example, in the previous page, this is a point cross. Okay. So based on this point cross, the first step is to extract some features. So because in the raw or the original point cross, it's a lot of points. If you directly process a raw point cross, it's going to be big computation load. So in this case, it first tries to extract some features. It's like maybe you like, as for each frame of the data from LiDAR point cross is 1 million of points. So after you do the feature extraction, it's maybe like only several thousands of the points. It can dramatically reduce the number of the points. So after that, you can do some optimization to get the change of your motion from two different timestamps. So by accumulating those motion change, you can infer your trajectory. So this is also a direct cleaning process. The positioning from LiDAR odometry is going to be drift over time because it's only a relative positioning. It's different from GPS. So actually, for the LiDAR odometry, it's always a big question, big problem. So for example, when I designed this course, I included the GPS, right? Of course, the second part is more about visual positioning. So if you want to make the LiDAR odometry to be clear, it's going to be another course. So I do not expect that you can really just generally understand the LiDAR can provide the directing, can provide the LiDAR odometry. So for example, okay, so in here we have two different colors of the points, red and blue. So for example, like I collect the LiDAR point cross. Okay, for example, if I get the LiDAR sensor on my top, so I collect the point cross at this point. So I move forward a little bit. So I still collect the 3D point cross. So for example, in this 3D point cross, we can infer the walls, infer some infrastructures. So based on some algorithm, we can infer a change. For example, how much I have changed from X, Y based on this two frames of data. So this is the two frames of the data, the red points and the blue points. Okay, this is generally how this LiDAR odometry algorithm looks like. How this algorithm looks like. So for example, this is the several milestones for for the LiDAR sensors, how, I mean, the whole cost change over time. By the 2007, okay, it's around like maybe 0.6 million Hong Kong dollars for this sensor. But at this stage, so I mean, for this, it's from DJI. This is the products. I mean, like iPhone 6, iPhone 9, iPhone 8. Currently, today is iPhone 16. Today, iPhone 16, right? So this is a similar case. This is DJI 1, DJI 2, DJI 3. So currently it's like DJI 20 something. So the cost is like below 10K already. Below 10K already. It's reduced almost every month. So this is the evolution of the technology. Like for example, like you can see from the, okay, this is the prices of the LiDAR. So for example, this company, okay, so this company is called Velodyne. So this company died already. So I mean, in the past 10 years, they make a lot of money. But I mean, because of the competition, okay, I mean, the commercial is quite competitive. So they didn't do the innovation. So finally, they died. I mean, okay, those new companies like DJI, they have the new LiDAR sensors. Maybe they not really died, but currently they have no market. I mean, like only make about like 0.1% something. For example, like DJI their LiDAR make about at least 10% something. So this, for example, the cost for this is only like 800 US dollars for this kind of LiDAR. Okay, this is the example. Like for example, okay, for the two frames of Pancros, okay, we can infer a change of the differences in terms of the motion. So for example, this is a, I mean, this is a directing process. For example, okay, at this timestamps. So x1 represents your states. So for example, your states x, y, z. Okay. So for the second timestamps, for simplification, okay, we only consider the x, y, z. So this, okay, move to this point. Next point, okay, there's some change. Okay, this represents the transformation from the point to this point, from 2 to 1, okay? So this is going to be an equation, x1, x2. Okay, this is two states, right? So also you can consider like, okay, if xk or x1, x2 is like two frames of Pancros, two frames of Pancros. So based on the LiDAR adoption algorithm, okay, this algorithm is represented as a function f. So the, I mean, the objective of this function is to infer the change of the motion based on the two frames of Pancros. Okay, so for example, okay, like how to understand? Okay, this is a, okay, this question. So this is a one frame of Pancros. This is another one. Okay, so I'm trying to identify a transformation. Like okay, do some rotation for translation, overlap, right? This is quite similar. Okay, I have the red points and the blue points. So find the rotation together with the translation to match the points. So this translation and this rotation is the exact the change of your motion. So it's corresponding to this transformation. So this is the basic principle of the okay, so for example, there are some quite mature algorithms, but still I want to emphasize the power of IC of the Python. So for example, those are some basic algorithms like to implement the LiDAR geometry. I mean, after class, okay, you can just search ICP from, okay, let's, for example, ICP and NDT are two typical algorithms to calculate the LiDAR geometry. So for example, if you learn from ChatGPT, so for example, like after lecture, you can take a try Gen AI. Oh, I mean, for staff, we have a lot of credits. We have 7K for each month for this. So for example, like if I want to give the example. CP. So the full name. So the full name of the ICP is like iterative coexist point. So this is the algorithm to to get the transformation, to get this transformation as I mentioned to match the two frames of the pancreas, right? So for example, if we search from GenAI, okay. So for example, okay, this is a quite, you can just quickly copy this code to the VS Code or from Chrome to replicate the demos. So for example, if you look into the codes, so for example, the input is the two brands of pancreas. For example, we just mentioned the green, the blue and red brand of the pancreas. So the input is the two frames of pancreas, right? So the algorithm output of this algorithm is the transformation between the two frames of pancreas. So for example, like for this, for this example code, it seems that it directly use some libraries. For example, this is the libraries to directly get the, okay, so for this one, applying ICP, so it seems it will directly do the, oh, this one, transformation estimation point to point. So it should be this one directly coming from some existing libraries. So for example, on the top, Open3D. So this Open3D is this is an open source library in the Python. You can easily have access to this library to replicate the LiDAR downstream process. So that you see, this is the power of the ChatGPT. How it can help you to learn instead of like that's just simply helps you to prepare the reports, right? You can also help you to prepare the codes to help you to, because for engineering lectures, usually I do not suggest like we only look into the equations. You may not have a good understanding about how these equations can be applied to in practice, right? So for example, for ICP, I just mentioned. So for example, if I want to reconstruct this room, for example, if I have LiDAR sensors, right, I can collect the LiDAR, the 3D pancreas from each of the positions. And based on the ICP, I can get the transformation of all the pancreas. It means you can accumulate all those pancreas. So in this case, you can build this map of this room. So later I'm going to have some videos. So in this case, let's see how the equations from the slide can directly get into the practice. So I suggest like in this lecture, because this course is quite free because it's like open book. Okay, we provide example codes to play with. Okay, please try to like adjust your mindset. Okay, try to use the codes. We provide some example codes. You can change the example codes after lecture based on the ChatGPT. You can learn from it. Learn from it. Okay, so we can just quickly get to the example codes using Python from ChatGPT to learn about the ICP. So for example, okay, this is example. So this is the examples like, for example, if we can infer the trajectory, infer the motion change of the LiDAR from different timestamps, if we accumulate, for example, okay, this color dots, this trajectory is, this is accumulation of the several dots. For several dots, this is the timestamps of the LiDAR collection timestamps. So based on this, we can get the trajectories, right? So by accumulating all those light point cross, you can easily get the map and simultaneously get your trajectory. And also you can do this based on the ICP from ChatGPT directly. Also, you can see, okay, this data set, this is in the US, but this one is in Hong Kong. Okay, so this data set is from our lab. Okay, from our lab. So you can see this should be in this one should be in TST, maybe. At least this is collected in Hong Kong. So you see the whole process is like kind of algorithm, very similar to ICP. Okay, so you can replicate those demos from based on the codes from ChatGPT. Maybe I mean the results may not as fancy as this one, but you can get the similar results to try to understand the LiDAR downstream. Okay, the power of the LiDAR downstream. But you see, the finally, okay, let's start this video. Finally go to the same location. See, there are some differences. This is the drift. Actually, finally go to the same location, go back to the point where it starts, but they didn't really exactly overlap with each other. That's why there's some drift inside. Okay, so this is LiDAR odometry. So if we say so, the LiDAR is quite stable compared with the camera. But in the future, we are talking about camera in the future. So, but the problem is like LiDAR is expensive, and also, for example, if this environments there are a lot of dynamic objects, it's also going to affect the performance of the LiDAR downstream. So this is generally the pros and cons of LiDAR. So this is another data set. So this is okay. This research platform is from AAE. So you see, we have several lidars. So those lidars can collect 3D point clouds. So for example, we collect the data from Hong Kong tunnel. Okay, we can see the camera and also the lidar. So this is the data set looks like. And also for this sensor kit, so this typically how the autonomous vehicles sensor system looks like. Okay, a bunch of cameras, a bunch of LiDAR sensors, and a bunch of GPS receivers. So this is an example like how to use the LiDAR to do localization for the cars. Okay, this is in PolyU. So for example, in the world of the LiDAR, it can have a good sense of the environments. So for example, there are some walls, some trees, so everything is in detail with the data collection from LiDAR. So with a help of LiDAR, we can do localization. Okay, so in this car, okay, it's fully autonomous driving. Okay, in this car at Polio campus with a super low speed. Okay, it's a super low speed for safety issues. So let's quickly go some other examples. Let's see the example like we do. So for example, if we build a map of the environments, and next time, if I just take image, and to do the matching, we can also do the localization. We try to matching the image we take with the prior map. Okay, we can also do the localization. Okay, this is about how to use the camera to localization. So for example, we have several trajectory. So the blue one is the ground truth. This is the visual geometry, and the yellow one is a real-time localization based on the matching, based on the visual matching. So for example, the idea is like, okay, so this is a real-time image. Okay, by using AI, we can do the segmentation. Okay, this is a chair, this is a wall, this is a monitor, this is a desktop. So based on this information, I can match this image with the map to see, okay, what is my location? Okay, this is the matching process purely based on the camera. Okay, purely based on camera. Okay, so you see, if you only based on the odometry, it will drift over time. So if you do the matching, the accuracy is much better. Okay. So this is a example in. So anyone know where is FJ05? Okay, FJ05 is a aviation lab. So see, let's see Dr. Xi, Professor Xi. So he do the demonstration at the FGO5. So I mean, based on the camera image with a prior map, we can do localization. Okay, this is only a demonstration. Okay, so let's move on to the next part about the coordinate system. I mean, by this point, we have introduced some basic knowledge about the Wi-Fi positioning, and also a little bit about GPS positioning, and a little bit about directioning, and a little bit about LiDAR downstream. So because this is still belongs to the first lecture about the concept, so I didn't dig into the equations. So from this part, we are going to talk about the coordinate. So for example, you say positioning. So the essence of the positioning is to determine the location xyz with respect to a given coordinate. Okay, this is the essence of positioning. Okay, determine the xyz with respect to a predetermined coordinate. So okay, the general definition of the coordinates. So a significant problem to overcome when using a navigation system is the fact that there are a great number of different coordinate systems worldwide. Okay, Big Ben. So anyone have ever been to Big Ben? One, two, Big Ben. Of course, right? Three. One more. Okay. So okay, for example, if I just define a reference point at the Big Ben. Okay, you can say the relative distance to the Big Ben is like 45 meters something. So if you want to make sure your coordinate system to be applicable to both US and maybe Asia area, you need a global coordinate system. I mean, the local coordinate is not good enough. So for example, for this one, this is the longitude, altitude. So this is the degrees for the latitude and for the longitude. This is a global coordinates. So for example, like this one, you can communicate with anyone in this world based on this coordinates because it's unique. But for this one, for the east, north, up, this is, this is not globally applicable because it's a local coordinates. Also, you can say, okay, so for example, there's a signal pole here. It's like several meters in the front, up, right. So this is the local coordinates. So this is not good enough for the global case. Okay, so those are the coordinates. So let's go back to like the problem is why we need to have the navigation coordinate system. For example, okay, I take flights from Hong Kong to San Francisco. So of course, for because you are all from AE, so of course we need to have some waypoints, right? Okay, the aircraft is going to fly through several waypoints. So if I fly to the waypoint K, so I need to know where it is, where I am, far away from this destination. Okay, for example, to Los Angeles. So I need a global coordinate system that is applicable to both Hong Kong and Los Angeles, right? So in this case, I need to define a global coordinates. So if I have the global coordinates, I can easily calculate the distance. For example, like this is the destinations, right? So xj, yj, xj, this is maybe the middle points. You can calculate this distance. So the question is, which coordinate you need to use? Okay, so we need to define some coordinate systems for the like especially for the long distance traveling with different purpose. So because for example for the navigation, if you look into the books about navigation, there are a lot of coordinate systems, maybe more than 10. But actually, in this lecture, I mainly talk about I mainly talk about 4 different coordinate systems. So the first one is the body frame. Okay, for example, like the drum, the body frame is fixed to the drum. The second one is called local frame, the ENU, the east, north, and the west frame. The third one is called ECI. Okay, Earth centered inertia. Okay, the last one is called ECEF. Okay, Earth centered and Earth fixed. This is the most typically use the coordinate system. I mean, by learning the full coordinate system is already good enough for the typical applications of the navigation purpose for example, like for the drones or for the aircrafts. Okay, so let's look into those definition one by one. The first one is the body frame. Okay, the body navigation frame. Okay, you can say it's a body frame or body navigation frame. So for this one, it's fixed at the usually it's fixed at the center of the drone. Maybe for example, this is a fixed wing. So this can be customized. Okay, based on your purpose. So it represents the orientation of the body to which it is connected. Its origin is described by the aerial vehicles. So sometimes it is the center of the gravity of the sensors. So it's based on your requirements. So the axis. So for the drones, usually usually the Z is pointing up. So for example, okay, if you follow this definition, pointing up to the complete of the orthogonal right hand. So orthogonal right hand is corresponding to XY. So the X B means body frame. Okay. So XB, YB, ZB means the body frame. Axis. X pointing towards the right to the direction. So Y is in the front. So of course X, okay, right hand system. Okay, the Z should be up. So this is usually the definition for the body frame. So for example, in some of the applications like attitude derivation, flight control system, or the simultaneous localization mapping purpose, we usually define the body frame system as like this. Body frame system like this. Okay, so this is for the body frame. Okay, so any questions?
To make sure, what's the details of the algorithm called PRO?
PRO?
Oh,
you mean
in the
video?
yes.
Oh, you can refer to the paper. Okay, that's a good question. Let's is our latest paper. Okay, for this one. This one?
Yes.
Okay, so this is the one from paper. If you're interested, I can share the paper to the. Okay, this is one for the latest research book from one for postdoc. If you read, I can share the paper to the platform.
Yes. Thank you.
Yeah, problem. Okay, so this is corresponding to the definition of the body frame. So for example, for the drones, okay, usually we define the body frame is fixed at the center, okay? The Y is pointing in the front, and X, okay, right hand system is Z. So the next one is called the ENU frame. So let's say the relative frame. So with the definitions. So the origin is usually defined by the users, for example. So okay, let's start with the next frame first. It's much easier to understand. So for example, this is ECI. So the ECI origin is at the center of the mass, of the Earth, and the X. Okay, with a given definition, for example, like SY lies in the equatorial plane but do not rotate with the Earth. So this, okay, remember this term, okay? This coordinate system will not rotate with the Earth, okay? So the x-axis, so this, okay, this is quite tedious, okay? XY is defined like this. So the Z is always pointing around the Earth's axis of rotation from the frame's origin at the central mass to the true north pole. So this is the true north pole for Z. So the main property for this one is that it will not rotate with the Earth. Okay, xy is defined like this. So for the second one, okay, so the ECF. So this one, the major differences of this coordinate system with the previous one is this coordinate system will rotate simultaneously with the Earth. So for example, okay, so similar to the ECI, except all axes remain fixed. So it means these three different directions all will rotate simultaneously with the Earth. It's fixed to the Earth. So x-axis points to 0, longitude defined by IERS. So this is the same with previous one. So for example, IERS is the Foreign Earth Rotation Reference System Service. So the Y is orthogonal with X, and Z is always pointing to the North Pole. So the 0, means the center of the Earth's mass. Okay, the 0, means the center of the Earth's mass. So for example, if we talk the XYZ, okay? So the XYZ, usually it's a big number. So for example, I say I in Hong Kong, okay? So usually for the typical values of the ECF coordinate system, it's a big value, maybe like 7 million something. Okay, maybe like XYZ is something like okay, so so for example, the longitude and the latitude of polio, I mean in Hong Kong is around latitude is around 22 degrees and the longitude is 114 degrees. But for the ECF, it's going to be a big number. But still, ChatGPT didn't tell me what is the exact location of, because I mean polio is a big area. Maybe it cannot associated with a given location. So anyway, I mean for this ECF, it's a big number. It's like maybe several millions, some big numbers for XYZ because the radius of the Earth is quite big. So in this case, the ECF coordinates, this is the global coordinate, okay, with respect to the center of the Earth. But the number is not physically understandable. So for example, the number is big, but if you look into this coordinate system, this is a local frame. So for example, okay, this June, for example, this is a June flying from this point, okay? So it will fly to this point. So ENU coordinate is going to be described. What is the distance the June have traveled in the north direction, east direction, and up direction? So this is much physically easier to understand, right? So this coordinate is a local coordinate system to describe so how the system move, okay, from the east, north, and up directions. So this is called local frame, ENU frame. So the definition is like this. So this is the relative of local frame. Usually the reference point. This okay, this blue point. The blue points, this blue direction. Okay, this coordinate is the ECF. So this is the longitude. This is the attitude. Okay, this is angles. So this is a reference point. For example, this Jones is fly from this point. So for example, this Jones fly from this point to this point. So we can directly describe the distance this Jones has traveled from east or north and up direction. So the purpose of defining the ENU is to provide a better understanding of the system movements, the system motion in the local frame. For example, like it's easier to understand, okay? So X in the north up and like east direction, how far it's move, okay, coming from the starting point. So its origin is described by a navigation object. So for example, this is the ECF, okay? So for example, we mentioned the ECI. So the ECI coordinates is never be used. Actually, it's defined, it's there, but we usually not use it. But for the ENU, it's quite easy to understand. So for example, ENU is used to denote the position because, for example, okay, if I fly a drones, usually I care about how far the drone have moved from east or north or up direction. But I don't care like how far it have moved with respect to the center of the Earth because it doesn't mean nothing physically. Okay, so this is the purpose of the ENU. So, for example, like robotic navigations, they usually use this. They usually use this. Okay, so if we put the three coordinate system together, okay. The first one, okay, of course, one more time. So the first one is the body frame, right? So the body frame is like fixed to the center of the Earth, right? So this is the ENU frame. Okay, this is with respect to the tangent space of a given point. So this is the center of the Earth, right? So this is the longitude, attitude. Okay, this is angles. Okay, I mean the units with units of the degrees. So the east, north, up direction. Okay, this usually we call it AR means the local frame. Okay, so this is the local tangent plane coordinates based on a selected reference point. So the east axis label X and the north is Y. That's why we call it ENU. Okay, east X and Y. U means up, corresponding to Z. So also let's rotate with the Earth, and importantly, this is useful to describe the motion of the objects on Earth's surface. So basically, we like to do some navigation purpose. The three coordinate system is good enough. Okay, the body frame represents, okay, for example, I take smartphone. Okay, the body frame is fixed in the smartphone. So the ENU frame is a local frame to describe the motion change. Okay, physically it's understandable. So for last one is the ECEF. Okay, this is a global frame. This is a global frame. So this is almost the last one for the coordinate systems, like how to represent the position and the attitudes. Okay, so let's finish this one before we take a break. So for example, before we start, we have some prerequisites like the matrix and the vector calculations and the unit or orthogonal basis of the coordinate system. So for example, like the notation definition is that, so matrix, we are use the bold uppercase, and vector with bold lowercase, and scalar with the lowercase Italia. So this is definitions for, okay, let's agree with each other, okay? So what is orthogonal basis? So for example, given a coordinate system, okay? Given a coordinate system, the three directions, they are orthogonal with each other, right? Three different directions, they are orthogonal with each other. So based on this, we can have three direction vectors. Three direction vectors, E1, E2, and E3, right? For each of the directions E1, E2, E3, they are orthogonal with each other. It means E1 vector multiplied E2 should be equals to 0. So this is the orthogonalities. And also, if we do calculate this one, it should be equals to 1. Okay, because this is the basic properties of the orthogonal basis of the coordinate systems. So for example, like we should have some basics. So for example, E1 vector multiply E2 vector, this should be equal to 0, right? So for any of the cross product should be equal to 0, okay? So any question for this one? Should be okay, right? Okay. So for second one, it's like basics for the calculations. So for example, if you want to solve the three linear equations with three unknowns, we have x, y, z. And of course, we can stack this into the matrix, right? So based on those three parameters, okay, the red part is the unknowns. So the blue part or the black part is the known variables. So basically, we can solve this equation by calculate the inverse of A. So just multiply A to the right side, okay? Multiply the inverse of matrix A to left side, we can eliminate this part. We can get A inverse multiply this. So finally, you can get the X. Okay, so this is the basics. So for example, like some conditions for the matrix multiplication. For example, if you want to matrix multiplication between A and B, so the columns of A should be the same as the rows of B. Okay, from your linear algebra, okay, you should learn this. And also the condition of the matrix inverse. So the A is a four rank matrix. Four rank matrix. It means each of the lines Okay, consider this matrix, they should be have the full rank. Okay, so the transpose of the, again, for this one is the identity matrix with size of n by n. Okay, so this is okay, right? For the basics for the matrix. So for example, you can do some basic calculations. So for the a plus b, it's like by, okay, do the summation of the each of the relevant components. And okay, if this is a 2 by 2 matrix, we can easily calculate the inverse based on this rules. So for this one, okay, you can just take try. So for the transpose, it's like flip back, okay, flip this left the low triangular part to the upper part to make flip. Okay, you get the A transpose. Okay, 1 minute, take try. Should be okay, right? Okay, so the results like this. So for the first one, it's like it's quite intuitive. You can directly, okay, just make a summation of the relevant components. Okay, like 1 plus 4, 3 plus 2, get 5, 5. Okay, so this is for this example, like, okay, just flip. Okay, flip this 7, 2, 5. Okay, flip, get this. Okay, so after you finish those basics, so for example, if a plane flight, okay, from Hong Kong airport to the Los Angeles, so how to define the pose of the flight in the space? So if you talk a point, okay, of a particle, so for example, the center is like ECF, okay, so X, Y, Z, so the G represents the global frame, okay, global frame. So for any of the particles, it can be represented by X, Y, Z. So the P means the particle, G means the global frame. Okay, represented by the XYZ. So define the pose of a particle in the ECF coordinate can be used 3 different variables. It's good enough, right? So the G denotes the global coordinate systems. So the problem is like if we are talk about a flight, if talk about flights, so we also need to determine. So for example, this the center of this, I mean, the body frame is corresponding to these particles, right? So if you only talk about the position, it's not good enough because also we need to have the orientations. So it means we need to have additional 3 variables. So for example, if you make some pitch or rotations, okay, how to define the rotations or the orientations? So in this case, we need to have the 3 additional variables. It's called orientation to define the pose. So this is XYZ together with the orientations. Together with orientations. So this is definition of basically the definitions of the pose. Okay, so take a break for 5 minutes. Okay, take a break. Yes.
But those guys asking because they they ask you questions that they know you can't answer, just wait. No, we do it. Serious. Show. What do you want? Put it in the toilet, run the toilet, put the dustbin. Fuck. Positive. Cost. Just put it in the toilet. Yeah, that's it. Right. Oh, what's it? God, I only want one. You don't have a piece of but they give it open the shop is all up. Like the whole thing, like the whole thing's full of one. Not just the shower is dry everywhere else. It's going to once cut. So
Okay, so let's go back. So I just mentioned, so for example, if you want to determine the pose, so pose includes the, okay, position, X, Y, Z, together with the orientation, so includes the pitch, roll, and yaw. So you need to have 3 additional variables to represent the pose, okay? So this is called position, okay? This is called orientation. So sometimes you can also call this attitude, ATTITUD, attitude, orientation. So this is the definition of the, so okay, so for the pose, it includes the 2 parts, right? So the first one, this is the position in ECF and roll pitch yaw. So for example, this is the aircrafts. So let's like, okay, let's, what to say, let's see the head. Okay, cannot do this. Let's see the head, let's see the rolling, right? Let's see the rolling corresponding to this axis. Okay, so it means the rotation with respect to the x. So this is the rolling angle. So for the like this is the yaw angle. Okay, so this is the pitch angle. So for example, if you take the flights, if the pitch angle is more than like 90 degrees, like approaching 90 degrees, it's gonna be crazier. So this is the pitch angle. So low pitch yaw, so the yaw angle is corresponding to the rotation with respect to the z-axis. So for the pitch angle, this is with back to the y-axis. Okay, so this is the pitch angle. So for this one, so since the body fixed coordinates CB means the body frame is fixed on the frame mechanics. So the coordinate transformation between CB and CG is the pose of the flight mechanics in the ECF frame. So how to understand this? So for example, okay, the ECF coordinate, this is fixed at the center of the Earth, right? This is fixed at the center of the Earth. And this body frame is fixed at the center of the fixed wing, the aircraft, right? So this fixed at the Earth, this is a global frame, right? So this coordinate system, we have a body frame. Actually, so the transformation from this coordinates to this coordinates. So the transformation means this is one coordinate, so this is another one. So transformation means how to translate, then you can rotate to make them to be perfectly overlap. So this is the transformation. So to make this, we need to firstly do the translation. So secondly, we can do the rotations, right? So by doing these two parts, it makes up the pose. So actually, the pose of this aircraft with respect to this coordinate system. Okay, so this is the pose of the aircraft, and this is equivalent to the transformation from this coordinates to this coordinates. So how to represent this coordinate system? Okay, so we need to combine both the rotation and translation. So first, let's talk about the rotation first. So for example, if this is a free vector, okay? Free vector. Free vector means there's no translation problem. Free vector, okay, free, okay? Can translate anywhere. So this is the ECF coordinates. So the green one means the transformation, okay, to this. This is the z-axis. So for example, the z and z, they are in the opposite directions. I mean, holistically, it's in the opposite direction. So this xb, yb, okay, so the transformation of the two coordinates is the pose of this aircraft with respect to the ECF. So for this free vector, okay, so if we define the unit orthogonal basis, so I mean the orthogonal basis, so we mentioned in the prerequisites, right? For each of the coordinates, we can have the orthogonal basis. For example, like for the ECF, you have the orthogonal basis, xgy, okay, orthogonal basis with three vectors, okay? This, okay, exg, uyg, and uzg. Also, and okay, so let's stop right here. So for this vector, okay, so the coordinates of this vector with respect to this coordinates can be represented by axg, ayg, and azg, right? I mean, to represent this vector, okay, represent this vector with respect to this coordinates, it's going to be axg. So axyz, g means global frame, okay? ECF is a global frame. So it's good at this point. So also this vector can be represented by this coordinate system. So this is going to be exb, eyb is the orthogonal basis of this coordinate systems. Okay, the orthogonal basis of this coordinate systems. So also this vector can be represented by the coordinate of this vector is ax, the three different components, right? In three different directions. So because a vector is a constant despite of a representation in different coordinate systems, so it means this is the orthogonal basis for this coordinates, right? So this is the coordinate of this vector. So because this is a free vector, I mean, despite of this representation, so this left side should be equivalent to the representation in this coordinates. So this is the orthogonal basis for these three directions. This is the coordinates for this vector, okay, in this coordinates. So because the left side should be equivalent to the right side, so in this case, in this case, if you make some movements, I mean, for example, like if we move the left side, okay, to the right side, we are going to get a matrix. We are going to get a 3x3 matrix. So this 3x3 matrix is going to associate this coordinate values with this coordinate values. And the transformation is only a rotation matrix. Because as we just mentioned, this is a free vector. It can free translate. Okay, can freely translate. So in this case, this position, okay, in G, global frame, okay, make a rotation, we can get to the position in body frame. So this 3x3 matrix, this is so-called the rotation matrix. So this is equivalent. This is equivalent to the rho and pitch and yaw. So the major differences is rho, pitch, and yaw is like defined by 3 degrees of freedom, right? So for this 3x3 rotation matrix, actually it's mathematically it's equivalent. But for this one, you get 6 variables, right? Because there are some orthogonal bases. So I'm not going to dig into this one. You can just understand, okay, so the rho, pitch, and yaw can also be represented based on this process with a 3x3 matrix. So in this case, for example, if you want to calculate the summation of the rotation, for example, I rotate this with this, how to summate this change of rotations. It's going to be the multiplication of the matrix transferred to the multiplication of the matrix of the 3x3 matrix. So let's start with an example, okay? For example, the position of a particle, okay, A in the body fixed coordinates. Okay, for example, if this is a particle, okay, this is a particle A. So the red color here usually means this is a unknown path. So the position of the particle A in the body coordinates, I mean this vector is a known variable. I mean this particle in this coordinate is a known variable represented by AXB, AYB, and AZB. Okay, in this coordinates. The second given, okay, the given path, the transformation between the CB is this coordinates. So the CG is this coordinates. As the rotation matrix R, GB, and the translation vector X means, okay, so actually this from this matrix to this matrix, it also includes the translation. So how to calculate the coordinates of a particle A in a coordinate G? So this is going to be quite straightforward. So for example, okay, this is the coordinates of these points in the ECF frame. So as I mentioned, so for example, for two coordinates, right? So first, to be perfectly overlap, okay? First, you can do the translation and the location. Also, you can do the location first and the translation. So the rule here is that, so for example, if you want to transform this point from one coordinate B to the coordinate G, so we do the rotation first, okay? Like, okay, rotation first, then translation. So as we mentioned, the rotation part is equivalent to the rho and ratio, okay? This is the 3x3 matrix. So first you do the rotation and translation. So this should be equivalent to the left side. Okay, so rotation first and then do the translation. So in this case, we can easily like transform one point from one coordinates to another coordinates, okay, by doing rotation first and put together with the translation. So this matrix represents the orientation, and this represents the position of this right, corresponding to this coordinate systems. Okay, so this is the definition. So in this case, like you see, orientation or position are all encoded with the matrix. It's good because this is, and the matrix is what the computer is good at. It can do the calculations easily with the MATLAB or with Python to do those calculations. Okay, so if you do a like an example, for example, previous page, this is known. Okay, this is unknown. And for this example, it's a inverse problem. So the given part is the position of a particle A is in the ECEF coordinates. For this point, okay, it's in the ECEF coordinates. So and also the transformation between the CB and CG is okay. The rotation matrix RBG. So RBG means the rotation from body frame from B frame to the G frame, and the translation is TBG from B to G. Okay, so the question is how to calculate the coordinates of the particle A in the body frame. It means actually it's this point in this coordinate system. What is the position? So this is actually corresponding to this vector. Actually, the position is corresponding to a value of this vector. Okay, so still we have similar equations. For example, like AG, the position of this point in the G coordinate should be equals to the position in the B coordinates plus rotation first, together with the translation. So it means the red part is the unknowns, right? So we can just move left to the left side. Okay, we can just keep this one. So then you can do the inverse. Just for example, if you move this part to the left side, you get less equations, right? So you can multiply the inverse of this matrix to the both sides. You can eliminate this one, right? So finally, you can get the equations from here. You can get this equations, right? So this is the cross transformation. Okay, transformation from one coordinates to another coordinates. So based on this rotation matrix and the translation vector. Okay, translation vector. Okay, so this is roughly for the we just finished the remaining parts for the first lecture, but no worries. Okay, we are still keep time. Okay, finish the lecture like around 6:10 something. Okay, so any questions for this slide? So still okay, like for the Wi-Fi fingerprint Wi-Fi range based positioning. Okay, last week we have showed examples. Okay, in here there's some comments because this is a comments for the codes we provide in a GitHub repository. Okay, those are the comments. So for example, like okay, for the codes, this represents the position of the first AP means access point. Okay, the routers. So the first, second, third, and the fourth APs. And okay, you can do this based on this Chrome-based editor. So this is the GitHub page, right? So you can find the code in the sample code, Wi-Fi RTT list estimation using a list script. You can just copy the codes to the okay. You can copy all Python code to this page. So just click this button, you can get the results. So for example, okay. So here the results x1 is corresponding to the location of the receivers So the red this represents the locations of the routers, right? Represents position of the routers. So you see there are several, the green dots, this is the final results. This is the final results, the green dots. So it's the initial gate. Because at the beginning, I have no information about where I am. So I just guess I at the 0, 0, 0 position. So the iteration process. So in the next slide, we're going to introduce this iteration process. So it will iterate from this point, this, and finally to converge. This process is a gradient descent process. We can also call it least square. So finally, it will converge to a given point. This is green points. Okay. Find the gem. Actually, in this code, this lines. Can you see the code? It's too small. So now this line. Okay. Animation, save, let's jab. Okay. See, let jab save here. Because the image, you cannot see the jab. So if you click this one, you're going to see the iteration process, right? Iterate, finally to converge to the point. So this process is called linear least square process. Let me try one more time, okay? Let me try one more time. For example, if you change, for example, like the initial guess, you see in the code, okay? So let's say corresponding to the location of the access point of the routers of the AP. So the distance, so for example, on signal, this is distance from the AP to the receiver. So for example, initial guess, this is the initial guess. Initial guess is you get because at the beginning you have information about where you are. So in this case, for example, if I set this to a big value, okay, you can see what we have. What do you see? So for example, actually the correct result should be here. So for example, if I set the initial guess to a big value, like I just set a value to 100 and for x and 0 for y and 300 for z. But I mean, you see the result is not correct. I mean, for example, if you brutally set root values for initial guess, you see it will, first it will go from very far from initial guess because I just said 300, 100 stuffs. So we converge to this point. Of course, it's not correct because just now we have shown this is the correct point. Any ideas why this happens? What I change is like I just changed to some root values. Any ideas? Jun, any ideas? Just say the first thing appear in your mind. So, for example, what I change here is that I only change the initial guess. So, okay, so yes, several rotors, right? Okay, for example, like those lines are all rotors. So, set the initial guess, for example. Okay, like those are rotors. Okay, the receivers, I receive signals, right? So I set the initial guess to it will convert to a correct solution, just as I showed just now. So if I set the initial guess, for the gradient descent, right? If I set the initial guess to a location that is far from this room, like to the canteen, to the block X, it will not converge to the correct solution anymore. So why? Any ideas?
So you need to relocate the original location.
Yes. So you need to locate the original locate.
Yes.
Again, take try.
The first step is to check the original location target, and then the correct location. depends on the original location and adjustments.
Yes. Yes, it's still the same something. Since you didn't say anything, this means like convergence with convergence. I mean results. It depends on you should get. So how to understand this phenomenon because so for example, okay, this is because as we mentioned, okay, so because this optimization problem, okay, this is more like for example, we have square distance one. So we have squares. Okay, because we calculate the distance from the routers to the receivers, right? So this is a square distance. So this is a four-dimensional problems, right? X, Y, Z. So for the web, you also have the clock bars. So the four-dimensional problem. So it's almost impossible to visualize the whole problem because it's more or less three dimensions, right? So this problem is a non-complex problem. So this means there are multiple local minimums. They have multiple minimas. So the same process is like you give an initial activity to the to apply the so to get like from this point at this point. Okay, it will converge, but it will converge to this point because it's already come minimum. So if you set initial gain swap to here, it will converge. Okay, gradient descent. Okay, go down, go down, go down. Finally, it will approach this point. So of the phenomenon is because the estimation problem is a non-convex problem. Non-convex means they have low minima. So in this case, so it means you need to measure. So this room, okay, you need to get in this room. It should be okay to converge to the solution. This is the phenomenon behind. So you can try. So for example, you try some smaller values to, like for example, just now we try some quite good values like 700s. So for example, we try like maybe it will converge to the correct. As it's not. You see, it will up to this point, right? Like several tens, it will converge to this. Actually, the ground truth, the correct location is here. It will not converge to the correct solution. Okay, this is a brief example to illustrate the problem. Okay. So, any questions for this page? Okay, let's do J. Okay, also let's do J. See, it iterates from faraway point and finally it will converge to this local minima. It's like converge from this to this, I graduate to this and to this. This is local minima point. Okay, so if there's no question, I'm going to finish this slide. Okay, so it's like 6 o'clock. You can take break for 5 minutes. Then we can quickly have some overview about the second lecture, okay? Take break for 5 minutes. Also, then take time your laptop. Okay, in terms of this phenomenon. Okay, so let's summarize today's lecture. Okay, so just now we have finished the you can say the first slide. Also, you can say the content for the first week. So in the next week, we are going to also have some Python code examples. So I suggest, because we have already uploaded the slide for the week 2, so you can just look into the slide, and I mean you can review the slide in advance, because we have several example codes for you to previous. So for example, in the page, so from page 48, so this is slide for week 2. So from page 48, so you are required to install VS Code. Okay, install the VS Code. So this is the editor. Okay, you can install the VS Code in the Mac, also in the Windows. So you can run this example in advance in your laptop. Okay, if possible. So in this case, you can just quickly have a understanding or have an overview about what we are going to learn from lecture 2. So for example, like based on this commands, you can install the VS Code in the laptop. Okay, based on Mac or Windows. So any of you are using your laptop with Windows 1, 2, 3, 4, 5, 6. Oh, it's crazy. Last year, like 99% is Mac. 99% is not Mac last year. So for example, if you install those, if you get some problems, okay, please raise the issue in a GitHub repository. So for example, if you like, for example, like, if you run this code, okay, in your laptop, if you have some problems, of course you can try to solve it from Google. Okay, if you cannot solve it, you can just, okay, I don't have access. So like here is the issue. Raise the issue in your computer, okay? Try. So this in front of PAs. So for example, you can raise the issue. So this will reply to you. Okay, reply to you in this GitHub. So for example, those are the questions I raised by myself. For example, I just raised this issue before this class. So our team has to answer these questions. So for example, like student A have this question. So we resolve the question by replying to your issue. So the student B can look in, for example, the student B also have this problem. They can just quickly go back, see, okay, the similar problem. In this case, we can collaboratively solve the problem, okay, instead of repeat the problem again and again. Have you raised the issue? Yeah. So for example, here is a new issue. So we should be able to find how to raise the issue. Yeah. So for example, here, PhD student raise a new issue. So okay, let's say something like, well, maybe you can try to just copy a snapshot, copy an image to here. So for example, when you try to install something, right, you may get some error. You can take a snapshot of the error to learn issues. In this case, here and try to understand, okay, what's the problem of your installation. So in here, AAE 4203, 24, 24, 25 semester 1. Okay, this is the name, this is the meaning of this name of this repository. You take image. Yeah. So for example, okay, so it's an image, right? So install a computer. If you get some problems, you can take snapshot and put and just upload to issues. So and also we provide examples. Actually, in the next lecture, we provide 2 examples. The first one is the code fitting for the linear case. The second one is the code fitting for the nonlinear case. So for example, okay, so let's see the code fitting from give us 7 points. How to fit in those points with your line. Okay, this is the linear real problem. And for the second one, we also have a nonlinear case. So for example, if we are going to fit, this is still linear case. We also have a nonlinear case. So for example, if you need to fit a linear function, for example, the exponential function maybe. So how to fit those points with a function like that. So the linear optimization problem. So all those examples can be replicated in the next lecture, okay, using the Python code. So any questions? So please refer to the slide in the blackboard, okay? So for the next lecture, so maybe if you look into slide, you can see a lot of equations. Okay, the equations we all are very physically understandable equations or figures or code helps you to understand. It's easy to understand. Then provide the step-by-step calculations for the linear estimation problem. So actually, I mean, the concept from my undergrad, I also learn the gradient descent, least square algorithms, but I don't know why I need to learn this. I can understand, okay, equations, iterate, calculation of the matrix inverse, transpose, but I don't know why I need to learn this. But that's why I continuously try to improve the lecture slide. So for example, in the provide a Python code, like you can have the intuitive understanding of the iteration process. Okay, for example, given initial guess, you are going to gradually approaching the destination. So this is going to help you to understand, okay, the gradient descent. Instead of lots of equations, okay, we provide the data examples. So to better understanding lectures next week, okay, let's take a look on the slide first, okay? So, okay, that's all for today's lecture. So any questions? It looks quite high. Any questions? No? Okay, so today's lecture. So I will stay here for additional 5 minutes. So if you have any questions, feel free to come, okay?直接在那个邮件上，没有收到那个邮件，结果哦，所以这里不是这个过的时间，它就是3。对啊，3点钟你应该每周都要听，单字就不一定，你以前知道好吗？其实有学过一点，对，学过，但是一个奶龟应该都能听，因为你们说到无人机导。对对对。对呀，这东西这个机制可以啊，那没问题啊。那你写个邮件给我，反正就像上次一样走那个 process，里面的话我可以算一算。好，我们到时候我们再找个项目去出这个钱。对，像上次一样，可以让那个走那个程序，然后让学校可以先付那个款。这个计算器，然后是计算器，我觉得这个蛮对，你可以问一下嘉豪。对，如果你不需要这么强的可能性够，就用低一点。但是如果你觉得有那个需求，就买贵一点的其他的。好，你们位置都排下来了吗？
对，还在
10月份对不对？
对10月初
好，好，好，对了，
QR814，
我发了。